When we say that hydrogen cyanide is a cheap way to extract silver from minerals, we're making a value judgment, not just about the prices of cyanide or silver, but about the social values of resource extraction and environmental safety. After all, cyanide dissolved in water is extremely hazardous to humans and to other life, so the decision to develop a method for silver extraction that relies on large quantities of toxic solution, and our decision to teach that method as a value-neutral application of electrochemistry, reveals a deep way in which non-scientific values direct scientific progress. The decision to treat the water and reduce the health risks is another telling choice. The Canadian Armed Forces put significant effort into environmental protection and remediation. Our choices in fuels, ammunition, site cleanup, and of course water purification all reflect Canadian values towards minimizing environmental impact and supporting sustainable development. Cyanide can be removed from wastewater by adding a hypochlorite bleach in slightly basic solution, resulting in nitrogen gas as well as bicarbonate and chloride ions. So if we find ourselves with 3.4 million liters of water with a cyanide concentration of 0.58 milligrams per liter, what is the minimum volume of 0.125 molar hypochlorite solution that we need to add to ensure complete decontamination? To answer this, we're going to need two pieces of information: the amount of cyanide in moles and the ratio of cyanide moles to hypochlorite in a balanced reaction. The first part of the question is straightforward enough. We can find the moles of cyanide according to its molar mass, 0.58 milligrams per liter times 3.4 million liters times 1 mole per 26.018 grams tells us that there are 75.79 moles of cyanide in that amount of water. For the next step, we'll need the ratio of cyanide to hypochlorite, and for that we'll need to balance the redox reaction. We start by separating it into two half reactions, one in which cyanide is converted into nitrogen gas and bicarbonate, and the second where hypochlorite is converted into the chloride ion. Let's start with cyanide. We begin by balancing the atoms other than oxygen or hydrogen. Here we need an extra nitrogen, so we'll need to write 2 cyanide are converted into nitrogen gas and 2 bicarbonate. Next, we balance the oxygen by adding as many water molecules as we need, in this case 6. Now we balance the hydrogen by adding both parts of an acid-base pair. We put the acid on the side that needs the extra hydrogens. Since the solution is basic, water is the acid and hydrogen source, and hydroxide is added to the opposite side to cancel out the extra OH in water. Finally, we balance the charge by adding electrons. In this case, we have 12 negative charges on the left-hand side and only 2 on the right-hand side, so we add 10 electrons onto the right-hand side. This half reaction is losing electrons, so it must be the oxidation reaction. And that means that hypochlorite is reduced into the chloride ion. The elements other than oxygen and hydrogen are already balanced, so we can move on to balancing oxygen by adding a water molecule. And now that we've introduced hydrogen, we need to counterbalance that with an acid-base pair of water and hydroxide. And we balance the charge by adding electrons to the left-hand side of the reaction, which is what we would want to see for a reduction reaction. Now that we have 2 balanced half reactions, we can sum them together after we multiply them as necessary to get the same number of electrons in both halves. At this point, we can cancel the electrons, the hydroxide, and most of the water to get the overall balanced reaction, where 10 electrons are exchanged per reaction. So now to get back to our main question, the ratio we needed for complete decontamination is 5 hypochlorite ions for every 2 cyanide ions. That means that we would need 189.48 moles of hypochlorite for the 75.79 moles of cyanide. The volume of 0.125 molar solution needed to deliver that many moles of hypochlorite is 1,516 liters of bleach. On top of the health risks associated with cyanide and with bleach, and the costs of bleach production that we haven't discussed, the remaining decontaminated products aren't exactly harmless either. Bicarbonate will equilibrate in water to produce carbon dioxide, and obviously that's not nearly as immediately toxic as cyanide, but is an environmental contaminant and a product of our social values nonetheless.